Shiming, are you ready?
Yeah.
Okay. Good morning, good afternoon, and good evening. My name is Kevin Xu. I'm a associate professor from Louisiana State University. Welcome to the 2021 World River and Delta System Source to Sink webinar series. As you probably already know, this webinar has been co-hosted by 4 organizations, including North Carolina State University, Louisiana State University, East China Normal University's State K Lab of Estuaries and Coast, as well as Utrecht University from Netherlands. So today, it's my pleasure to co-host this webinar for Dr. Shiming Wan. And of course, Paul Liu has been organizing everything for the webinar. So before we talk about today's webinar, I want to remind everyone there is a YouTube channel. All the talks have been posted on this webpage. So feel free to watch the videos. Feel free to use the material for teaching and research purpose. Also, in China, there's a Bilibili website. So all of you can watch the videos there for your convenience. If you use Twitter, please follow us. We actually have a Source to Sink account on Twitter. So lots of seminars have been announced on this Twitter account. A heads up for next week. So next week, there will be a speaker, Dr. Sen Gupta from East China Normal, the State K Lab. So the title of this talk will be Land Reclamation in the Anthropocene, Spatial Temporal Trends and Drivers of Major Coastal Geoengineering Projects. This is very close to the end of the year, so looking forward, let's talk about the year 2022. So we already scheduled a large number of speakers from all different kinds of universities. Right now, we already scheduled speakers from January to mid-March. And those schedules are still tentative. And if you are interested to give a talk, or if you have someone in your mind you would like to recommend to give a Source to Sink talk, feel free to contact Paul Liu or me, and then we can schedule the talk for you. And remember, the overarching theme of this webinar series is on the Source to Sink system. So basically, we care about what's going on from the top of the mountain, through the drainage basin, to the river mouth, all the way to continental shelf, slope, and rise. So it's a very large spatial scale. Okay, so now let me introduce Dr. Shiming Wan. So Dr. Wan received a BS degree from China University of Geoscience in 2001. And then in 2006, he received a PhD degree from Institute of Oceanology, Chinese Academy of Science. So back in 2004 or 2005, during which I was a PhD student and Shiming was also a PhD student, we had some collaborations. So I actually learned how to do X-ray diffraction from Shiming and other researchers from the Institute of Oceanology. So that was a really nice experience. And then after that, I collaborated with Shiming on a few papers, but we never see each other in person since then. So it's been 16 years, so it's amazing. Okay, so after graduation, Dr. Wan did a postdoc at Institute of Geology and Geophysics in Chinese Academy of Science. And then he did some research as a visiting scientist in different countries, including United Kingdom and France. He also served as a shipboard scientist in multiple IODP field trip. And now Dr. Shiming Wan is a research professor of marine geology at the Institute of Oceanology. So with that, I would like to stop sharing. And then Dr. Shiming Wan, you can start your talk now.
Okay. Thank you, Chloe. This one. Okay, can you hear me?
Yes, very good, very good.
Okay. Good evening, good morning, everyone. And I'm Shiming from the Institute of Oceanology, Chinese Academy of Sciences. And many thanks for Kehui's introduction and Jinpu's invitation. And today, I'm very glad to talk something about the tectonic evolution of Asian great rivers. And I will show two examples. One is from the Bay of Bengal, and another is from the South Yellow Sea. And I will show how the provenance change relate to the tectonic evolution and the river evolution. And this work, many people contribute to this work, including my students and colleagues, and also include Christophe Collin and Christophe Collin from the Paris Saclay University, and also the Peter Cliff from Louisiana University. So, as we know, the most important tectonic event on the Earth during the Cenozoic is Tibetan uplift. And with the collision of Indian and Asian continents at about 50 million years ago, and the Himalaya and the Tibetan plateau progressively uplifted afterwards, especially during the Oligocene and the early Miocene. So this important Asian deformation change the Asian topography from the west tilting to the east tilting. So finally resulting the river reorganization and the monsoon evolution. And these uplift processes produced the largest sediment source-to-sink system in the world. So there are many great rivers in Asia, including the Yellow River, the Yangtze River, Pearl River, Red River, Mekong River, Irrawaddy, Sarwin, and the Ganges, Yarlung from Putra River and the Indian River. And in totally, and all these only 5% of the land area on the Earth's surface contribute around nearly 30% of the solid or dissolved loads to the world oceans. So this is very important in the global energy and the material cycle. And the topic one, I want to talk something about the formation and the evolution of Yarlung River evolution. And at present, the Yarlung River just flow easterly through the south of Himalaya and rapidly flowed to south at the eastern syntax of Himalaya and mixed with Brahmaputra River, and finally drains into the Bay of Bengal, the northern Indian Ocean. So this is the present situation of these South Asian rivers. However, how it evolved during the geological past, whether it responded to Himalaya uplift, so these are remained questions. So in 2004, and Clark and his colleagues presented a famous hypothesis about the Asian river capture and its links with uplift of Tibetan plateau. And based on the field observation and digital elevation model, they suggested that during the Oligocene, the Yarlung River and the upper reach of Yangtze River just were parts or tributaries of the Red River and flowed into the South China Sea. And in contrast, during the Miocene, the early Miocene to late Miocene, and because of the uplift of Himalaya and Tibetan plateau, and the Yarlung River was captured by the Brahmaputra and the Irrawaddy and flowed into the Indian Ocean. So this is a very nice story. However, we need more evidence. And here I will give a brief review for this provenance change and the river evolution based on pressure studies. And the provenance study on the Shigat sedimentary rock in the South Tibet and shows that the Yellow.Yangtze River ever flowed westerly to Indus River at 20 million years ago, and reversed its direction to easterly at 4 million years ago. So this means that the Yellow.Yangtze River ever flowed into the Arabian Sea. And in contrast, according to Robinson and Brackley studies, they also based on the provenance study using the zircon dating and heavy minerals and in central Myanmar and also the Suma Basin. And they suggest that late Eocene, the Yellow.Yangtze River just flowed easterly to the Irrawaddy and captured by Brahmaputra in the early Miocene. And a recent comprehensive review suggests that the Yellow.Yangtze River didn't flow easterly or westerly to the sea, and is just ever an internally drained basin before the Miocene, and then joined in Brahmaputra until the early Miocene. So this is consistent with Spicer's tectonic model of a very flat and low topography in the Himalaya region before the Miocene. However, all these studies is lack of the exact age constraints. So in comparison with the continental records, the marine sediment is more continuous and has much better age controls. And as we know, the Bay of Bengal is a major sink of sediment evolved from Himalaya erosion. And there are many DSDP, ODP, LDP drilling in this region, and including the DSDP 22, ODP 11.6, LDP 353, 354, and 362. So these are very useful materials. And the previous studies from Galley and Chen just suggest using the strontium lithium isotopes at DSDP site 218 in the Bay of Bengal, and also LDP site U15, U1480 from the legal fan. This is close to Bay of Bengal. So all these studies show that very stable the provenance contribution, sediment contribution from Himalaya since around 19 million years. So this means that the Himalaya source of the river should have much older history than the 19 million years. And the remaining questions are when did the Yarlung and Brahmaputra river system formed and integrated into the sea, and whether it linked to Himalaya uplift. So we need long-term and continuous sediment records that can extend to the early Miocene to Oligocene, because these periods are the critical period that Himalaya and Tibetan region experienced rapid tectonic uplift. And so we can indicate, we can test whether there occurs drainage reorganization. So the materials we used from ODP Site 758 from the southern Bay of Bengal on the Indian Ocean ridge with water depth of around 2,900 meters. And the core length is around 249 meters and with bottom edge of around 37 million years, the late Eocene. So I should say that this side is on the ridge, so it's much shallower than the surrounding basin, and the turbidite sediments can be excluded from this to this area. So the material is very fine-grained and very fine-grained sediment that's transported by the surface current from Himalaya or surrounding the land areas. So the methods we used including clay minerals, the strontium lithium isotopes on the clay silicate fraction and terrestrial flux. And this is the lithology and ID model for this study site. And it can be subdivided into two units. Unit 1 is for the upper 122 meters. This is characterized by lead fossil woods with clay. The unit 2 is for the lower part is the lead fossil and calcareous lead fossil chalk. So in general, the lithology through the core is homogeneous and very good materials for the paleoceanography reconstruction. And the age model is based on the delta and the calculus that fossils. This is shipboard data. And this is the result show the variation of clay minerals and the strontium lithium isotopes at the start site since around 37 million years. And we can see that the terrigenous mass accumulation rate, the terrigenous flux, and the chloride elite content just slightly increased between the 35 to the 80 million years, and rapidly increased since around 80 million years. And moreover, the lithium isotopes that show that became more negative between the 37 to 22 million years, and it became the positive between the 22 and 80 million years, and then remained relatively stable since 80 million years. And in contrast, strontium isotopes show different patterns that it increasing, that show an increasing trend since around 22 million years. And in general, in overall, we can see that the provenance change, significant provenance change at the two time. One is 22 million years and 8 million years. So in order to constrain the sediment provenance, we firstly should consider the potential sediment source to this study area. For this area, the potential sediment source including the peninsular facies and Dagon traps, and also Himalaya source rivers, that's the Ganges and the Yellow-Yangtze River, the Brahmaputra River, and the Irrawaddy, and also the Sibamsu, and also the Andaman Nicobar Ridge. So this is the lithology for these different end members, different sources seems very different, especially for the Himalaya source region. The rivers is characterized by the very old, the metamorphic rocks and granite sandstone. And so the western product of the Himalaya source regions, the modern days is elite chloride rich, the clay minerals. And for the Indian Peninsula, especially Dagon traps and the Andaman Ridge, this is basalt and also the basic rocks, ultra basic rocks. And their wisdom products is the smectite rich, the clay minerals. So this lithology is very different. This is the base for the provenance tracing. And we use the clay minerals to trace the provenance and use the ternary diagram of smectite, elite plus chloride and kyanite, and to compare the clay mineral composition of our study site with the potential sources. And there is a basic simple assumption that the clay mineral composition of the potential end members didn't change largely during the studied geological past. And this is basically reasonable just because of the lithology of the different part is very different. And also the significant change of this composition may mostly reflect the river organization or the drainage area change. So we can see that from our data, this blue one, the yellow one, the green one, these sediments became from older to younger. And we can see that the sediment source changed from smectite rich and member, the Dagon trap and member, this Andaman Ridge and member. And for younger sediment is more overlapped with the GB river system, this Himalaya source river system. So the sediment source is very clear from the Indian or Dagon to the Himalaya source rivers through the studied time. And in comparison with clay minerals, strontium lithium isotopes is more reliable in the provenance tracing because of they are dominated by the lithology or the age of the parent rock rather than the chemical wisdom processes. And we can see that for the older sediments that before the Miocene, the blue ones, that it seems the study sample is a mixture between the peninsular lysis and the Suibumasu and the member block. And for the Miocene, from the 22 million years to 8 million years, the yellow ones is seems the more addition of the Irrawaddy and the GB river system. This is from the Himalaya source rivers. And for the green one, this is the youngest. Since around 80 million years, they're mostly overlapped with the Irrawaddy and the GB. So since that time, the Himalaya source rivers dominated the sediment provenance. So together with above discussion, we can see that the source change, sediment provenance change at 22 and 80 million years. And here we also show the proxy leader isotopes and the smectite to chloride elite ratio. So we can see the 22 and 80 million years, the sediment source change significantly. And this indicates the Himalaya source rivers formation and development, and both of which consistent well with the two-phased uplift of Himalaya as the early and late Miocene. So this is reconstructed by fossils based on the elevation change of Himalaya erosion. So in contrast, we also note that the global climate indicated by the isotopes, that the global climate and the regional climate didn't change significantly across the 22 million years. So the climate change is not the important factor, especially for the 22 million years, the source change of the study site. And in contrast, since around 80 million years, the global cooling and also the intensification or the weakening of the Indian monsoon may also contributed to the enhanced physical erosion in Himalaya and the more elite rich materials to the Bay of Bengal. So this the climate also maybe is another factor besides the tectonic forcing since the late Miocene. So this is our suggests that before the Miocene, we can see that the sediment mainly came from the Indian peninsula, and during the early Miocene, and since the early Miocene, the Himalaya source materials, rivers source materials initiated, and since the late Miocene, the Himalaya source rivers finally established, similar to present situation. So the conclusion is that the provenance study suggests that sediment from Himalaya to Bay of Bengal became more important and stable since 22 and 80 million years ago, respectively. And considering the timing of major tectonic and climatic evolution in South Asia, the Yarlung, and Brahmaputra and Irrawaddy rivers have been initiated in the early Miocene and fully established in the late Miocene. And second, I want to talk something about the East Asian rivers, the evolution of Yellow-Yangtze River, both of which are the most important rivers in East Asia, and because it delivers huge sediment to the eastern China seas. And however, their history are also not so clear. And for the Yangtze River, the Yangtze River history seems very old. We can see the ranging from the Eocene, the 40 million years, to the early Miocene, the 23 million years, to the late Pliocene, the 3 million years. And in contrast, the Yellow River seems much younger, and most age focus on the middle Pleistocene, about 1 million years. So notably, all these results are most of came from the continental records, only very few just from the marine sediment. And as we see that the Eastern China seas, including the Bohai Sea, Yellow Sea, and the East China seas, are the major sediment sink of Yellow River and Yangtze River. So we can see that this is ideal region to trace the history of Yellow and Yangtze River in the geological past. However, unfortunately, there are very few. There are most no the DSTP, ODP, LDP drilling in these regions. Most because this seawater is too shallow, And the longest LDP core at the East China Sea. In the East China Sea, there are kilo 12 and the U15, U1429, U1428 only extend to the late Pleistocene. I attended this cruise LDP 346, and the age, bottom age is around 0.4 million years. So this is very young for the age. And we know that we have many that the very short term the sediment records from the Yellow Sea to East China Sea or Kilo 12, and this most focus on the short time scale, especially during the Holocene or the late Quaternary. And for the long term, the sediment record most came from the river mouth of Yellow and Yangtze River. For the Yellow River, just because this is more easier to drill, and for the Yellow River, we can see that the oldest sediment is around 3.7 million years, and this study is very good, and they focus on the chronology and the transgression in Bohai and the Yellow Sea. And for the Yangtze River, and there are also many drill sites for this area, and they focus on the provenance and suggest the formation age for a young age of the Yangtze River evolution, around 2 to 3 million years. This provenance studies mostly based on the zircon dating and the heavy minerals. And in comparison with the river mouth and the basin on the shelf, the basin on the shelf is more stable and less disturbance, and thus ideal to trace the long-term evolution of river flux, river evolution. And however, there are very few such kinds of long sediment cores that extend to the pre-Quaternary. And it's lucky that during the 2013, the CSDP-01 was drilled in the South Yellow Sea, and the water depth is around 53 meters, and recovered the core length is around 300 meters with bottom edge of 3.5 million years. So this sediment core has a very good edge control, based on the PMAP. And the methods this study we used, including the clay minerals, strontium needle isotopes, and focus on the silt to clay fractions and the terrigenous grain signs and the microfossils identification. So based on the core description and grain signs and also the microfossils identification, the lithology or sedimentary facies for this study core can be subdivided into two parts. For the upper unit 1, the upper part, upper 82 meters, that is characterized by the shallow marine facies. We can see the abandoned the marine species foraminifera and also the orchestral chords. And for the lower part, the unit 2 from 82 to 300 meters, that is older than 0.8 million years, and are characterized by the nearshore terrestrial environment that also including the floodplain, noxious river channels. So this is very interesting. So one question is that is this huge change in sedimentary facies from the continental to the marine environment? This huge change is it just a local phenomenon or regional phenomenon? So this is important. We should make sure this is a regional phenomenon. And then we compare the snot site with other cores, and we don't have too many very long-term the sediment cores, but they still can compare together, and we can see that. So from this QC2 and NH01 also from the Yellow Sea, South Yellow Sea, and the BH08 is from the Bohai Sea. So we can see it's clear that all these sediment cores show the general trend of large scale the transgression from the the continental to marine environment, from the Yellow Sea, from the Bohai Sea to Yellow Sea. So this is a very large scale, the transgression through the Eastern China Seas. So this is a regional phenomenon. So the further question is the transgression is caused by global sea level change or regional tectonic subsidence. And we know that during the Quaternary, the global sea level just fall down. The fall down, especially since around 1 million years, just because based on the sea level reconstruction. And so it cannot explain the large scale, the transgression in these marginal seas. So it only can be influenced by regional tectonic subsidence. So what caused this regional tectonic subsidence? And we suggest the Minzhe uplift for this zone played a significant role in this river, in this sea level change. And this zone consists of Mesozoic to Precambrian igneous and metamorphic rocks, and is tectonic controlled by the constrained by faults from China, Eastern China to Korea, and it uplifted as a highland due to volcanic eruption in the late Mesozoic. However, it subsided below sea level in the Quaternary. However, we emphasize that not all the parts of Minzhe uplift just subsided now, but some parts still just uplift above the sea level. For example, the Jeju Island is also part of this Minzhe uplift. So it acted as a key barrier for Pacific seawater intrusion into the Yellow Sea. So this part is very important. And just together with previous studies on the evolution of the Minzhe uplift, we suggest that subsidence of Minzhe uplift at around 0.8 million years just induced the large-scale transgression of Yellow Sea, Bohai Sea thereafter. And there is also, for the Jeju Island, we can see that the large scale, the very frequent volcanic activity in this island that occurred since around 0.9 million years. So this also supports the evolution for the Minzhe uplift subsidence. And this is the result variation, so the variation of clay minerals and also the structural medium isotopes for the start side since around 3.5 million years. And we also observe the smectite content the rapidly decreased since around from 40% to 20% since around 0.8 million years. And the medium isotope also became much negative since around the same time, the 0.8 million years. And structural isotopes show reverse pattern as the medium isotopes. So all these the clay minerals and structural medium isotopes suggest that the obvious change of sediment source for the start side since around 0.8 million years. So we compare the sediment composition with the potential sediment source to the start side, including the Yellow River, Yangtze River, and we also compare with the Paleo Yellow Yangtze River and the Paleo Yellow River. The Paleo Yellow River we just treated as the lures, the source of the lures, because we know that the major source to the Yellow River is from the Lurs Plateau, and the Lurs and the problems of Lurs didn't change much during the Quaternary. They may suggest that stable problems for the Yellow River. So we can see that the sediment delivered to the start side before the 0.8 million years were mainly controlled by the Paleo Yangtze River. Now for the upper part, for the younger sediment, since around 0.8 million years, that it more overlapped with the Yellow River. So this is very interesting, it's very different. And for the clay mineral also shows a similar result. And since around 0.8 million years, the sediment came from the Yellow River. It overlapped with Yellow River. However, for the for the older times before the 0.8 million years, the sediments overlapped more similar to the early Pleistocene Yangtze River, the smectite ridge. So this is very different for the modern Yangtze River and the older Yangtze River. We also kept we also have some sample from the Nanjing and during the middle Pleistocene. So the Yangtze River sediments more smectite rich. So this is interesting. And the problem summary is that the sediment source that before 0.8 million years ago were mainly controlled by the Paleo-Yangtze River, and later was dominated by the Yellow River. So this suggests that the Yellow River sediments have influenced the Yellow Sea at least since the middle Pleistocene. So they may be also linked to the river evolution. And for the Yangtze River, the integration age is very old. And Humboldt study using zircon dating of Yangtze graphite sediments and indicates the modern Yangtze River was established at least before 23, the early Miocene, after which it flowed into Subei Basin, close to the South Yellow Sea, is near to our study site. So this means the old Yangtze River ever directly drained into the South Yellow Sea during the Miocene and possibly also during the Pliocene. So this is the big background. And for the Yellow River is much younger. And there's also some continental studies and shows that, for example, here is from the Salmon Gorge. For the Salmon Gorge is the last gorge of the Yellow River draining into the sea. And it shows that the zircon and also the cosmogenic nuclei shows the age of around 1 million years. And also this is from the Gonghe Basin is from the northeastern Tibet and indicates the formation age of Yellow River around 1 million years. So this study just shows the age is very similar, very close to the age of our study, the provenance change. However, they just explain this the development or birth of Yellow River as the cause of global climate change. And just because we can see from the oxygen isotope that the increased the variability of the global climate since the 1 million years or since the MPT, the middle Pleistocene transition. Since that time, the climate, the variability increased, and then the global erosion may increase, and then this is caused or induced the river birth, the Yellow River birth. Or this is the explanation. However, we think that this explanation cannot explain the very good agreement in timing of the provenance shift from Yangtze River to Yellow River, and also onset of large-scale regional transgression in the Yellow Sea at the middle Pleistocene. And so we think this cannot exclude the possible influence of tectonic deformation besides climate change. Climate may be a factor, but we cannot exclude the tectonic factor. So there are many studies suggest that the stepwise uplift of Tibetan plateau drove the initiation and the evolution of Asian monsoon and river systems. And for example, the beginning of the Earth deposition and the Yangtze River, and also the Asian drying that occurred around 22 or 23 million years, and also since around 8 million years. And then how about Yellow River? And Yellow River is much younger. However, how it linked to the tectonic evolution? Is it an exception with the tectonic driving? So this is a problem. This is a question. So there, the uplift history of northeastern Tibet is still highly debated. However, there are still some studies, especially from Professor Li Jijun and also Fang Xiaomin, suggest this is a very, very comprehensive review published in Quarter Research. And many studies show the dating of the late Siloy hydrologic basin sediments and tectonic geomorphology of the northeast Tibet just has a stepwise uplift at around 8 million years, 3.6 million years, 2.6 million years, and 1.8 million years, and 1 million years, and 0.15 million years, and all this resulted in the rapid incision of Yellow River. So this suggests that the Yellow River evolution also strongly related to the tectonic uplift of the northeastern Tibetan plateau. So moreover, we also observed another interesting phenomenon, that the reduced sediment contribution from Yangtze River since around the Middle Pleistocene. We can observe this point, and this is consistent with the southward shift of Yangtze River mouth at the Middle Pleistocene due to the tectonic subsidence of eastern China coast and the Minzhe uplift. So this is supported by the seismic data from the eastern China coast. That this South River, the Yangtze River, southward shift. So we know that the present Yangtze River is just draining into the sea in Shanghai, but in the past, especially before the Middle Pleistocene, it drained to the South Yellow Sea. So this southward shift or southward move of Yangtze River mouth, so is related to the regional tectonic activity. This is important. And based on all these studies and the reviews with the consistent timing in transgression through the East China Seas and the Provenance change, and also the Yellow River integration and the Yangtze River mouth shift at the same time at around 0.8 meters. So this suggests a chiral link. So this is not coincidence. And the northeast Tibetan uplift and also the tectonic subsidence of eastern China coast at the same time. And so this may be the cause for this evolution that we observed. And so at last, I just present a hypothesis that's to describe the whole story. And the uplift of East Tibet and the regional extension of faults in the North Plateau region, coupled with the subsidence of the basins in the eastern China. So these processes not only opened a path for the Yellow River that flowed to the east to the Yellow Sea, South Yellow Sea, but also removed the barrier, the Minzhe uplift, the barrier for the Pacific water intrusion, northward intrusion to the Yellow Sea and the Bohai Sea since about the 0.8 million years. So this is just a hypothesis. But we need more the scientific drilling, especially the ODP drilling in these key interesting regions, and to test this idea. So that's all. Thank you.
Thank you very much. Okay, any questions? You can unmute yourself. Go ahead, ask a question. If you prefer to use the chat box, you can type the question in the box as well. I want to open the floor to everyone. Any questions?
So too long talk.
Shiming, let me start a short one. This is a great talk. I really learned a lot, particularly, the evolution of the Yangtze and the Yellow River, and also Gulf, the Bay of Bengal. So before 0.8 million years, Yellow River, and you said it's 3.5 to 0.8, the Yellow River kind of in inland. Is any opportunity before 1.8 Yellow River flow to the Bohai, maybe not a Bohai Sea, maybe a Bohai Lake, and make some great accumulation there?
Yes, this is a very good question, and many people propose this question. Yeah, this is just one important problem is that we only have the one sediment core from the South Yellow Sea. This is a problem. But there is another core from the Bohai Sea. The base edge is around 1 million years. Is published by Xie Shi and Zheng Quanyao, and they also shows the very similar result. Just since around 0.8 million years, the sediment provenance just change to the Yellow River. So Yellow Sea also have similar phenomenon. Yeah.
So, I mean, in Bay of Bengal, you also show similar something like a 22 million, and that's the the Indian continent, with Eurasia, the collision, and also the uplifting. So, I mean, the shifting from the Irrawaddy to Ganges, this has happened. I can't remember at what time.
You mean the shift from Ganges to
no from
Ganges.
the Irrawaddy. Before you see there's more in Andaman Sea, they're now shifting more free will from the Ganges. When the Ganges Brahmaputra begin to make a major contribution to Bay of Bengal.
Yeah, that's a good question. But from our study, we cannot identify the details of rivers, such kinds of Ganges, Brahmaputra, or Irrawaddy, which river just deliver more sediment to the start side, because these sediments is all these rivers that originate from Himalaya, their source is very similar. You can see I show that from the Climatic and also the strontium needle isotope. The more easy, the more clear difference is that is between the Himalaya rivers and the Indian rivers. Yeah, we see the signal that the shift from Indian or Andaman Ridge materials to the Himalaya source rivers at 22 million years. Yeah, so we suggest that the Himalaya rivers may just initiated or developed since the early Miocene.
Well, good. Thank you.
Okay, we have a question from Shiming Wan. You can go ahead and unmute yourself.
Okay, thank you, Professor Wan, give you a very nice talk. I have a question about the clay minerals sometimes used for the provenance study, sometimes used for the climate change. I want to know, I'm confused, when it can be used to provenance study, when can be used to the climate change for the indicator of both.
Thank you. That's all?
Yeah, that's all.
Yeah. This is also a problem that we when we started using the clay minerals. Yes, we should consider this because as you know that the not only the province but also the climate, the influence, the weathering processes, and so usually we cannot dependent only on the clay mineral, the assemblage. We usually just combine the method from clay minerals and also the isotopes. So both of these methods I think should be more reasonable, more reliable. So I'm not sure if you understand what I say.
Yeah, I think so. We need to consider another information or indicator to consider
Yes. This is this is one problem for the clay minerals. Another problem is also I also propose that is that the how to determine the composition, how to determine composition of the end members is very in the so long time scales. The problems and the members change. How to determine this is also a big problem that is not easy to fix. And but we try to explain sometimes. Yeah. Thank you.
Yeah, thank you.
Yeah.
Okay, any other questions? I can ask one quick question. So, so Shiming, you mentioned the Minzhe fault. So my understanding is that it's a long ridge from Zhejiang Fujian province to probably South Korea. So it's a large tectonic feature. So when that fault was really high in the geological past, how would that impact the coastal ocean circulation? For example, was there crucial warm current during that period? If so, was the coastal current blocked by this fault? So if this is a really large morphological feature, was it subaerial or subaqueous?
So you mean that the faults, how the faults relate to the current?
Yes. Yeah. How does that impact the coastal physical
current.
oceanography?
Yeah, this is a good question. I'm not sure if there are people that consider this one. Yes, yeah, you know that because you also study this region in the past, and the most people study the coast current just focus on maybe the Holocene, yeah, but very few they consider the so long term how the current evolved. Yeah, I'm not sure for the faults, for the Minzhe uplift, the faults, how the activity for these faults evolved during the past is still unclear. It's very unclear. Yeah.
Okay, thank you. Any other questions? I see Paul Henrich here. So Paul is from Louisiana Geological Survey. So Paul, do you have a question? I'm not sure if he is still around. Okay, any other questions?
Anyway, great. Shiming, how about the Taiwan's sediment contribution to the East China Sea? Because if you see that East Asia, the tectonic tilled down, is this also affect the Taiwan sediment to the East China Sea or Okinawa Trough or something?
Yeah, this is also an interesting point for the Taiwan sediment influence on the East China Sea. But to my knowledge, the Taiwan, you know, the Taiwan uplifted at around 5 to 3 million years ago. Yeah, so from the present study, especially during the Holocene, the Taiwan sediment contribute largely to the Aquila Trough. Yeah, this is what we know, but we don't know how it influenced during the past. But to my knowledge, I think that it should be very minor contribution to the Yellow Sea, to the South Yellow Sea. That is too far. Yeah, you know that is too far. Maybe then some sediment, very fine grain sediment, can be transported by the warm current, by the western boundary current, the northward transport from the Taiwan to the Aquila Trough, and even to the to the South Yellow Sea, but this should be very, very less influenced, I think, because you know that the Yellow River, the Yangtze River, the discharge is very huge and very close to the area.
Okay, any other questions? Yeah, based on Shiming's talk, sounds like the study of the Yellow River between 2 million to probably 20 or 30 million will be a grand challenge, because we don't even know if the Paleo Yellow River was 100% inland river or was a part of the tributary of another large river. We don't even know if the Yellow even flowed into the Bohai and the Yellow Sea. This is a grand challenge. I think the coring technique will be a huge challenge, because those two large rivers empty a huge amount of sediment to the Asian marginal seas. And because of that, in one side, it gives us a super high resolution to study Holocene, right? You can study lots of high, but in the meantime, it's a grand challenge for us to study the deeper, older geological time scale, because lots of sediment are so recent and it's so costly to drill a deep hole.
Yes.
Yeah, that's a grand challenge.
Yeah.
Okay, any other questions? Okay, thank you so much. We had 100 participants. 100. Yeah, that's
more than 100. Yeah,
more than 100.
very good.
I keep watching. Yeah, we at the time we had more than 100 participants.
Okay.
So Shiming, you are probably